A GLP-1 peptide drug can pass a purity check, hit its expected total mass, and still hide a flaw no technical measurement will reveal. A single swapped amino acid, an oxidation, a fragment that shouldn't there. So how do scientists prove that a 30 residue peptide is built exactly the way it should be? Hello, I'm Raghuveer Singh Parmar, Director Scientific Affairs at Resolve Mass Laboratories, and we work with pharma and biotech teams to characterize GLP-1 peptides down to individual amino acids. Today in this video, one of our GLP-1 peptide mapping series will walk through enzymatic digestion mapping, the technique that breaks a complex peptide into readable pieces in about 8 minutes. Why mapping matters? So why does peptide mapping matters right now? In barely 2 decades, GLP-1 receptor agonists have gone from niche diabetes drugs to some of the best-selling medicines on the planet, now reaching into obesity and metabolic disease. But each of these molecules is a long foldable peptide chain, far more complex than a small molecule tablet. As generics and biosimilar race to market, sponsors must prove their peptide is structurally identical to reference, and regulators won't accept a clean purity number alone. They want evidence at the level of individual amino acids. So, what exactly is an enzymatic digestion mapping? At its core, it's a structured workflow that uses enzymes as molecular scissors. Each enzyme recognizes specific amino acid residues and cuts the peptide only at those points, producing fragments that are predictable and easy to read. For example, trypsin is the workhorse here, cleaving after lysine and arginine. Glucy cuts at glutamic acid. Chymotrypsin targets the bulky aromatic residues like phenylalanine, tyrosine, and tryptophan. And ASPN cleaves on the N-terminal of the aspartic acid. Pick your enzyme and you control exactly where the chain breaks. You might ask, why not analyze the whole peptide at once? The problem is complexity. Push an intact GLP-1 peptide into a mass spectrometer and you get congested, overlapping signals with modifications blurred into the noise. It's like proofreading a paragraph printed on top of itself. Digest that peptide into defined fragments and the picture transforms. Each piece gives a clean resolved mass. The spectra simplify, and anything out of place, an oxidation, a substitution, a stray impurity stands out. Smaller pieces, sharper answers. So what does a good map actually gives you? 3 things. First, sequence confirmation, direct evidence that the amino acids are in the right order from one end of the chain to the other. Second, impurity and modification detection, the ability to catch oxidation, deamidations, or a single residue that's been swapped, the kinds of defects that quietly compromise a peptide. And third, regulatory grade data, audit-ready documentation that holds up in an IND, ANDA, and biosimilar comparability package. Those 3 outputs are exactly what reviewers expect to see. Multi-enzyme strategy. Here is where experience matters. A single enzyme almost never gives a full story. Cut only with trypsin, and any region poor in lysine and arginine yields fragments that are too big, too small, or sometimes missing, leaving blind spots. The fix is a multi-enzyme strategy. and a second enzyme like glucy, and it cleaves where trypsin couldn't filling the gaps. So better still, the fragments overlap, so the same stage of sequence gets confirmed two independent ways. Trypsin plus glucy is a classic pairing for near complete coverage. Of course, it's rarely that clean in practice. 4 challenges come up again and again. Incomplete digestion leaves missed cleavages, so you tune the enzyme ratio, time, and conditions. Over digestion shreds the peptide into too many pieces, so you control incubation and quench on time. Low coverage calls for complementary enzymes, and raw LC-MS data can get overwhelming, which is where high resolution instrument and expert review on their keep. At Resolve Mass, we have watched a single missed cleavage artifact send a team chasing an impurity that was never there. The skill is knowing what's real. So how does it come together at the bench? It starts with the sample preparation, purifying and desalting so salts and contaminants don't poison the enzyme. Then digestion under optimized pH, temperature and time, followed by quenching, usually a quick acidification to stop the reaction at the right moment. The fragments go on to LC-MS, where chromatography separates them and mass spectrometry weighs and sequences each one. Finally, the software maps every fragment back to the chain, and scientists review the coverage and skip the prep, and everything downstream suffers. So what should you walk away with today's discussion? Enzymatic digestion turns one unreadable peptide into clean, legible fragments. Your choice of enzyme controls exactly where the chain is cut. A multi-enzyme strategy is what gets you near complete coverage, and careful sample preparation paired with expert review is what separates reliable data from noise. If you are developing a GLP-1 analog, a generic peptide, or a biosimilar, and you need a CRO partner who treats characterization as the real science rather than a checkbox, Resolve Mass Laboratory supports small and mid-sized teams from first method through regulatory submission. Subscribe so you don't miss the rest of the series of the videos, and drop a comment telling us which peptide you are working on and which kind of session you want us from our side. Thank you so much for watching this session, and see you in the next one. Until then, goodbye for now.